לא הייתי לפני. אבל כאילו... כן, אני יודע מה זה, ברור.
No, there's no box, so there's supposed to open there. I just give him the answer. Because
Did you make it very full? Did you get like another slot? Not Italian? Or the
no, I will have to do.
זה כמה הקלטים של שאר קודים. משם פחות או יותר התחיל הסמינר.
The mailbox for your pencil is downstairs. No, it's on the first floor in the dorm.
תשובה? תשובה? אני מנקד את זה. ממש. זה לשבת פה על הספה.
אני לא אהיה פה. יואו, אבל להעיר אותי כל יום.
כמעט.
What we'll do today is apply the theory that we developed for encoding of multi-dimensional stimuli to the retina. And it's roughly based on works of Attic and Edlich. I mentioned these citations and I'll put them on the model. So, put on the title. So, what are the main features of the theory that we want to derive. One very important feature is convergence from photoreceptors to RGCs. As I mentioned in the presentation last week, outside of the fovea, which the fovea is special, outside the fovea, the ratio is about 100, so maybe about factor of 10 in each direction.
10?
Yeah, but in each direction it's 10 times 10. So what can we expect based on what we've discussed more generally?
In the context of convergence?
Yeah.
We should not direction. Direction.
The
Direction
first,
or
yeah, right. So actually, encode only high components with highest variance. Now, this reminds me that I actually didn't finish the topic of properties of the visual stimulus. So I need to go back in my notes and I'll leave this here. And we have maybe 10 or 15 more minutes to discuss what are the components with the highest variance. Okay? So, yes? Oh, yeah. I thought I did. In fact, it did turn off, I think, for a short while. Maybe I pressed it twice.
It's still on now.
Yeah, I see, but there's a delay in the response of this thing. That's what makes it confusing. Yeah, I think now it's turning off. Okay. So, we need to go back to discuss the structure of visual stimuli. Putting this aside. For statistics, natural statistics. Of visual stimuli. By the way, is someone taking notes? Great. Okay, so I already discussed with you the fact that natural stimuli have some symmetries in them. Translational symmetry is very important. I will not repeat all the definitions, but what I wrote is that the correlation function of the visual stimulus in two positions, x and x prime, is really a function of the difference in these positions. And that alone implies that if we go to Fourier space, we diagonalize the correlation function. So the linear transformation that diagonalizes the correlation function is a linear transformation going from representation in real space to Fourier space. Or in other words, the oscillatory functions are principal components of the visual stimulus. And the way I wrote it is that S of k, S of k prime, once we Fourier transform the signal into S of k and S of k prime, so let's put a wiggle here, this is the Fourier transform, this has to be diagonal. Now, diagonal, when we have complex functions, it's convenient to us to define it in this way, k plus k prime, not k minus k prime. So k here and k prime actually have to be with a minus sign, they're the same up to a minus sign relative to each other. And this function, which in fact, this function is the Fourier transform of this function. I will not go into the details, but if it is not clear to you, you should think why this is true. This function is the Fourier transform of this function. It's really representing how much variance there is in different spatial frequencies. So the larger this G tilde, the larger the variance in that particular K. Okay, so, and this is what we call the power spectrum. Now, as I mentioned, we also will make the rough assumption, not precisely true, that there is rotational symmetry in the natural world. And if that is true, then g of x is really only a function of the magnitude of x. And when we go to the Fourier space, g of k is really only a function of the magnitude of k. And so once we've realized that, we can ask, how does g of k look like for natural stimuli? And you can do this exercise yourself. You can take some images. You can even roughly do it with one large image, you know, and do its Fourier transform and look how much power there is in different Fourier components. And if you do it on more images, you'll get more smoother statistics. And if you do that, you'll discover that there is something very universal about the behavior of this quantity. Why am I saying universal? The concept of natural statistics is, of course, somewhat vague. What do I mean by natural statistics? Do I mean a photograph taken in nature? Do I mean a photograph taken in this room? There are some features which are quite robust. And so what you will typically see is what we call a power law. That if we plot as a function of log k, we plot log g. Sorry, here I'm doing it in real space. So log magnitude of x, and here's log g of x. Okay. You will find, and you will kind of do this empirically, you will find that for a large range of x's, very large range, this falls on a straight line on a log-log plot. Straight line on a log-log plot means that it's a power relationship, right? So this means that g of x is proportional to x to the power minus eta. And maybe I will continue here. And I will not prove this, but this implies also a power law in Fourier space. It implies that g of k is proportional to k to the minus 2 plus eta in 2 dimensions. We're dealing here with 2-dimensional objects, okay? So these two, let's say if you take this function and calculate its Fourier transform, that's what you get, okay? Now,
G of x is a density?
well, g of x is a correlation, so there's something interesting here in the way you think about it. Real space versus Fourier space. In Fourier space, different Fourier modes are independent of each other. So g of k just represents how much power there is in different spatial frequencies. In real space, different locations in space are not uncorrelated. And what g of k represents is how much correlation there is between 2 points in space and how it decays with distance. So it decays with distance like this. And eta, by the way, I didn't tell you what is eta. So eta, well, what I read is that it's about 0.19. I'm not sure how seriously we should take the 9 here, but 0.2 is the typical value that you would get. It's small. Now, There is one very important feature in a power law. Do you know what it is? There is something special about this kind of function. Scale invariance, yes. What this means is that if I would show you, if you know that, these are the characteristics of visual stimuli. Okay? Maybe you don't know how much power to expect in a signal overall. There could be an amplitude that depends on the light condition and so on. This power law, you know that that's the case. And I show you two versions of the image, one in one scale, and then I zoom in into some different scale of the image, or zoom out. You would not be able to distinguish on which scale you're looking, because in all scales it looks the same. There's no characteristic scale in this function. Right? An exponential function, if it was exponent of, say, minus k, it would have to be exponent of minus k divided by some characteristic k, meaning that the correlation decays beyond that characteristic k very strongly. Here there's no characteristic scale. Can you tell me why visual stimuli have no characteristic scale in them?
Can you explain what it is again?
Yeah, so if I plot, for example, the function exponent of minus x divided by x0, I'm doing it in non-dimension. Then that function has a very characteristic scale in it. That's the scale x0.
It's a sort of time constant? Time like a time constant?
It's similar, but here it's spatial.
Okay.
But let's just think about it mathematically. I show you this function. I tell you that something has this function. Now I show you this function in different. I change the scale of the axis. You'll be able to tell. You will be able to distinguish between this and this and this, right? If you take a power law and you look at it with different scales of the axis, you will not be able to distinguish at which scale you're looking. So this seems to tell us something fundamental about visual stimuli, that indeed there's no characteristic scale in them. And I'm asking whether you can hypothesize why that's the case.
Why is this the case?
That there's no characteristic scale in the visual stimulus that we're getting. All scales appear in it. Well, that's the meaning. That if I would take the visual, now it's a rough statement. It's not precisely true. But if I would take the visual an image and then zoom in on it and show you a part of it, it would have the same statistics as the whole image.
But you're talking about natural stimuli.
The natural stimuli.
When I look at this area around.
Right. In this room, it's probably not correct, because there's a scale of meters which characterizes this room, right?
So
But in more natural stimuli, it's
jungles?
maybe, yeah. Empirically, it's an observation that you see in the statistics, and I just trying to think why that might be the case.
Maybe many things in nature are like
So maybe the objects
fractals.
in nature themselves are like fractals. They have some
Yeah,
similarity.
I
But I'm not sure that that's the reason. I think there's a better reason.
Because we get near and we go.
Exactly. We see objects in very different distances from us. The objects can be at, very close or very far. So naturally, the objects in the visual scene appear in different sizes, and I think that's the main reason that this is true. Although I'm not sure I couldn't find a work that actually explains why this is the eta, for example.
As an individual, you can distinguish between the size if you, I don't know.
So, for example, if you were looking at an image with people in it, you would obviously be able to tell at which size you're looking, because you know that people have a size of about 1.7 meters, and so you would be able to identify the scale of the image, right? But the claim is that at least at the level of these more rough statistics, the correlation function, the image is self-similar. Images are self-similar. And I think, again, that that's the main reason is the distance, but I'm actually not even sure about it. But in any way, this is an empirical observation. And people often tell you that natural images have a 1 over k square dependence in the power law. You see that it's actually not k to the 1 over k squared, it's actually k 1 over k, square minus 0.19. But roughly speaking, it's about k squared, 1 over k squared. Okay, I want to clarify even a bit more what I said when I wrote this, that the principal components of the visual stimulus are the Fourier components. So I just want to emphasize this even more. We'll see it coming up again when we go back to our simplified model of the retina. So the translational invariance means that the principal components of visual stimuli are Fourier modes. And what I want to remind you is that we can write Fourier modes in different ways. Often mathematically it's convenient for us to work with complex functions, something like e to the I dot kx. So in 2 dimensions, if we were in 1 dimension, it would be sat ikx. But in 2 dimensions, a function like this is like a function that oscillates only in the direction of k, right? Because this thing is independent of the projection of x into directions which are perpendicular to k. So this varies. If k is a vector in this direction, we have a function that oscillates in this direction. It does not depend on this direction. So this is a sinusoidal varying in this direction, and the magnitude of k tells us what is the oscillation frequency. And and I just want to remind you that if you feel uncomfortable with complex functions, given that the visual stimulus itself is of course a real function, this is really a combination of, we can write this as a combination of 2 functions, cosinus k x plus I sinus kx, and we can construct functions which principal components which have which are purely real, because we have another principal component which is e to the minus ikx, and it has exactly the same variance, and so any combination of these two is also a principal component. And since this one is cosinus kx minus I sinus kx, then the sum of these 2 functions is also a principal component. Since the cosinus, the difference between these 2 functions divided by I is also a real function, and it is the sinus. So we can construct the different phases of the oscillation by different combinations of these 2. So this is just... Yes.
Why in the k direction and not the x?
Well, I view this as a function of x. I think of k as fixed. We can choose k to be anything we want. And then this, I view this as a function of x. And then I'm asking, how does this depend on x? Okay? So first of all, I see that if I add to x something which is perpendicular to k, it doesn't affect this function at all. Which means that this function takes, if this is the direction of k, this function takes constant values in each one of these lines. Right? Because if I add to x, x is a position on this board. If I add to x something which is perpendicular to k, it does not affect this function.
Why?
Because it's a projection of x of k. So if I project on k something which is perpendicular to k, if I write x, if I add to x some delta x which is perpendicular to k, delta x times k will be 0. Okay? Now, if I go, on the other hand, in a direction parallel to k, then this is simply k times x, and then I get an oscillation. So this is just how to write, Fourier components in 2 dimensions. But we actually will not do it. We will work, as you will see, in a 1-dimensional version to avoid these more delicate points. And so now, after saying all this, we can go back to coding in the retina. And what we really need is, going back to this point, our prediction based on what we've done last week is that if the coding in the retina follows the principles that we discussed, then the retina the convergence from photoreceptors to RGCs should discard all the principal components with the lower variance, and we know now that these are the Fourier modes with high frequency. So we expect the retina, the projection from photoreceptors to RGCs to maintain only the lower spatial frequency.
Why higher frequencies are
Because this is what I told you here, that the variance is a monotonically decreasing function of the frequency. Okay. All right. So this would now be lower spatial frequencies, which are the principal components with the highest variance. Now, let's ask ourselves for a moment, suppose that the retina is implementing what we call the WPC solution. Remember, the WPC solution was the one where each output unit encodes the component of one principal component independently of the others. So, if the retina uses a WC solution, then each RGC encodes the amplitude of a certain Fourier function in the image. And I'm putting in here a question mark because I would like to ask you, if that's the case, what does that mean for receptive fields in the retina? Yeah.
So they have to be huge, no?
Yeah. How would they look like?
Like the whole image.
Yeah, they would look like Fourier functions which span the whole image. They would look like oscillatory functions that span the whole image. So if that's the case, then the receptive fields would be Fourier functions and that would mean that they would span the whole image, and we know that that's not the case. The receptive fields of retinal ganglion cells are very localized, and they're symmetric, and like they have a circular symmetric structure. So the question, real RGC receptive, this by the way, the receptive field. Receptive fields are localized. They're spherically symmetric, but okay, that's not going to be so important because we will discuss a one-dimensional version. But there's one other feature that we know that they have, and this is that they're all the same. I mean, they in different parts of the image, you have different cells that one cell maybe responds here, another cell responds here, another one responds here, but they all have the same structure of the receptive field. Okay, so this is what we call the translationally invariant when we discuss coding. Now I have to say that in fact it's not precisely true. We discussed the fact that in the fovea receptive fields are smaller than in the periphery. But if we take a patch of the visual signal outside of the fovea, this is what we will observe. So now the question is our theory, what is going on here? We worked hard to develop a theory for coding, and we had the WPC solution, and it predicts something which is completely incompatible with what the retina does. So what might be a solution for that? Should we throw away everything we've done?
Maybe do like the Fourier.
Well, we had a theory. The theory told us what the receptive field might look like.
Ignore
It
biology.
doesn't really tell us.
Why?
Because up to some unitary transformation.
Okay, very good. So remember, the theory actually didn't tell us that the WPC solution is the solution. It told us that we can take the WPC solution and apply to it a unitary transformation. And so what we need to ask ourselves is, given that freedom, can we take the WP solution and apply to it a unitary transformation such that we will get something that looks like that? Okay? And in fact, as you will see, not only can we get something like this, these requirements are sufficient. If we assume that this is what the retina is doing, then this will be sufficient to tell us precisely what the receptive field should be. We need to look for a unitary transformation such that we will get from the WPC to something that obeys these rules. Now, why might the retina work in this way? And not in this way? Yeah, maybe in terms of the hardware it's easier. It means that you need to have projections only locally in each part of the retina from the photoreceptors in that area to the ganglion cells, and you can just repeat that structure again and again. If the retina would implement something like this, it would be immensely more complicated. It would mean that each retinal ganglion cell needs to receive inputs from all the photoreceptors, and also the connection from each retinal ganglion cell to the photoreceptors would have a completely different structure for each retinal ganglion cell. Whereas in this solution, it's the same architecture just repeated in different parts of the retina. So this is what we now want to understand. So maybe I'll just write down the solution. Well, it's not all. The problem is if we don't assume this, we cannot predict actually what are the receptive fields, because the theory allows us to use any unitary transformation. Now, what I'm saying is that once we predict that, there's still a huge number of possible. I mean, it could be any function, right? The receptive field could have any structure, and the theory does tell us now exactly how it should look like. So the theory is still going to tell us a lot. Okay? And you know, we know that the theory tells us interesting things, that depending on the amount of noise at the input, we go from the structure of the receptive field should change. And in fact, as I argued, told you last week, this is what we see that happens in the retina, that the structure of receptive fields changes from center surround to just center. And the theory predicts that, as you will see. So let me just write down the solution to this problem. That's the freedom to apply a unitary transformation. And having said that, we'll now dive into the theory and look at a more precise mathematical model. So we discussed now a one-dimensional model of the retina. And the idea is going to be that we have our input layer, which is the photoreceptors, and we have n of them. And then we have a smaller number of retinal ganglion cells. We have m of them. we have our weights, which are W, so this is I, this is J, Wij transpose, as we did all the time. But to make life easy for us, I'm going to assume that n is an integer multiple of n. So there's an integer number of photoreceptors per ganglion cell. And I'm going to make some additional mathematical simplifications, which will just make the theory more easy to deal with. They're not fundamental. Okay, so one additional assumption, and the assumption is that the ingredient that I put into the model is periodic boundary positions. You'll see what I mean by that. I mean by that more than one thing. For example, one thing that I will mean by that is that if we ask what is the statistic of activation of the photoreceptors, so we discussed the fact that this has to be only a function of the distance between two photoreceptors. But now by saying that I'm applying periodic boundary conditions, it will mean that, say, the correlation, I will assume that at the inputs, the correlation function between this and this, which is the same as the correlation between this and this, the same between this and this, is also the same between this and this. So the correlation between this and this is the same as the correlation between this and this, and the same, let's go one more step, this and this. And now, but I'm going to assume that in the inputs, it is also the same between the correlation as the correlation between this and this.
Okay.
So it's as if it's all on the ring. Now, of course, it's not true for natural images. For the images we see, there's no correlation between what I see here and what I see here. But it just will make the theory more elegant, and it will only affect. So it will only affect. The only thing you need to write is periodic boundary condition.
Yeah, but this, so it's hard to formulate it.
Yeah, and the other implication of my assumption of periodic boundary conditions will have to do with this aspect. So we're going to write in a moment that we expect the receptive fields to be translationally invariant. It means that the projection between this ganglion cell to the photoreceptors is the same as the projection of this ganglion cell to the photoreceptors up to translation, but in fact this one has to go, like when it goes in this, if I would have another one here, it would actually connect to something here. And that's, of course, again, not the structure of receptive fields in the retina, but since we know that we're going to get localized receptive fields, the only place where this matters is the edges. And so we expect that the theory will predict correctly the receptive fields throughout most of the visual scene, except perhaps for the cells which are at the edge, and then we don't care so much about that. Okay, so, and what we gain by making this assumption is simply mathematical elegance in what we will write, which will be complicated enough as it is. Okay, so this is what I assume about boundary conditions. Now let's talk about. Yes.
Why does this periodic boundary condition mean that in the edges the projection would be translational?
Well, because what this means again. Suppose that you know how this ganglion cell connects to the photoreceptors. Now the translation invariance means that it immediately tells you what everyone else does. But now the question is, what do I do when I reach the edge? So with periodic boundary conditions, it means that I assume that the receptive field of this cell actually, since this cell projects to cells that are to its left, this one, maybe let's take one that is here, it needs to project to cells to its left, but there's none, so it actually projects to something over here. That's not realistic, right? In the retina, a ganglion cell which is sensitive to what's going on at the edge of my visual field is not actually also sensitive to what's happening in the other edge.
Isn't it connected to all of the photoreceptors anyway?
Yeah, but the structure of the, but in fact, we're going to end up with localized receptive fields where these connections decay or only have significant values only in a small region. Okay, so what else do we need to define in the theory in order to apply what we've learned in the past 2 weeks? We need to define the input statistics. But we know what is the input statistics of natural stimuli, and note that in our theory, all we care about is the covariance matrix. So this is actually exactly what I described to you in the beginning of this lecture. So I will assume that it's Gaussian. That's not true for natural images. We might discuss this a bit on, we will discuss this a little bit on Thursday. And I assume translational symmetry of the input statistics. And that implies, as we discussed, that the principal components are Fourier modes, Fourier functions. When I say modes, it's just another way of saying Fourier functions.
But didn't you just say earlier that the correlation is some kind of power law?
So that's the principal components are the Fourier components.
That's because of the translational symmetry.
Yes. The power law just tells me what, if we go to Fourier space, it tells me how much variance there is in each one of them. And that's an empirical observation which is not arising from translational symmetry. It's an additional feature.
But this is incompatible with the Gaussian.
No.
No?
No, it's not incompatible with the Gaussian statistics. You could construct your statistics by saying that in each Fourier mode, you draw the amplitude as a Gaussian variable with a certain variance. Okay? And that's actually exactly the definition of these statistics. Now, if you would go back to real space, that would imply also Gaussian statistics, which is yeah, it's a linear transformation, and it will be translationally invariant, and so it will depend only on the distance between any 2 points. Okay? So, it's a bit, I don't want to continue here, so I will continue here. So I just want to finish defining the problem, and then we will take a break. So we know what are the Fourier modes for this. The Fourier modes, or the Fourier functions, in this discrete formulation with periodic boundary conditions are simply the following. Each Fourier function has an index k that tells us which one it is, and then there is the index j. Maybe I would put here I want to put here an I because I used I for this layer, and I'm now here. I'm asking what is the statistics of activation of the photoreceptor. On the other hand, I cannot use I because I is the square root of -1. So maybe I'll put here an L. But if I end up writing J, then tell me, because J is what I have in my notes, and I think it's better to use something else. So 1 over square root of n, and then e to the 2 pi I here is the square root of -1, k L divided by n, where k can go from 0 to n minus 1. These are necessarily the principal components of any correlation matrix that it is circulant, that's the periodic boundary conditions, and the fact that it's translationally invariant. You discussed this with Neta. So now we need to decide. So one thing that I want you to note here that K here plays the role of the spatial frequency. The larger K, the more oscillatory, more rapid the oscillations as a function of L. But because of the discrete nature of these points, something a little bit weird happens. So if I take k equal to 0, this is a function which is constant. If I take k equals 1, this is a function that does one oscillation over this whole range. Now I continue to increase k, and I get more periods within the range. But at some point it actually reverses, because you can see immediately that when k here goes from 0 to n minus 1, but k equals to n minus 1 is exactly the same as writing here k equals minus 1. I could have think about this as minus, if I put here for k n minus 1 or minus 1, I get the same function. So k equals minus 1 is the same, it has the same oscillatory behavior as k equals 1. So in fact, when we look at k going from 0 to n minus 1, the more natural way to think about it is that the spatial frequency is increasing up to the middle, and then it's decreasing again. Okay, and the reason this is all compatible is that due to the discreteness of these points, you actually cannot distinguish between a function that does, one oscillation here, or one that does so rapidly oscillating that it actually, like if you have, say, another way to say it, if you have an oscillation which goes like this, you cannot distinguish between it and a function which is constant. In the same way, you cannot distinguish k equals n minus 1 is the same as k equals minus 1.
Why would you say that the slow ones are in the middle? Or that would you say
The fast ones are in the middle. The fastest ones are in the middle. So if you go to, when you reach k equals n over 2, you have a function which just alternates between plus 1 minus 1, plus 1 minus 1, plus 1 minus 1.
you could also think of it as a function that goes like...
But you could also think about it as a function that continues to oscillate more rapidly, but it oscillates so rapidly that it finishes more than one oscillation between one point and the next one.
Like
So
you always shift your... So how can you say which is faster?
well, the fact is that when you discretize a function, you probably heard about the Nyquist limit and things like that. You cannot distinguish. There are certain frequencies that you cannot distinguish.
Just look like the one with the lowest absolute value.
Yeah. So for us, just in the way we think about it, you'll see how it matters in a moment. It will be more natural to think about the low frequencies as the ones close to 0 and the ones close to n minus 1.
It's just a decision. It's not something...
It's in a sense it's a decision. There are some subtleties that I don't want to go into in how I formulate it, because I need to have pairs. These are complex functions. I need to have for each. It's more than a decision, because if I said, for example, if I tell you what is the variance for k equals 1, it will have to be the same variance as for k equals n minus 1, because these two functions, e to the plus 2 pi I L over n and a to the 2 pi minus I over L over n, have to have the same variance. Otherwise, I will not have two principal components that are real, that are real. These are subtleties. Let's not worry too much about them, and just believe me that that's the correct way to do it. And you'll see now how it matters. So what I'm going to assume for the eigenvalues of the correlation matrix, lambda k, is based on what I've just erased, the power law behavior of the variance in natural stimuli. So I want to write here 1 over the spatial frequency to the power 2 minus eta, but I will write here a large k and not the small k, and now I'll explain to you what is the large k. Okay? So the large k will go, so when k goes from 0, 1, up to n over 2 minus 1, and then up to n minus 1. I could just as well think about it as 0, 1, n over 2 minus 1, and then start to decrease, to write negative values, minus 1, minus 2, minus 3. And so the k I will define as this quantity, or actually the absolute magnitude of this quantity. So,
שהם לא רואים.
okay, so I will write it down here. K is equal to small k for k going from 0 to n over 2 minus 1, and then it will be k minus n, or so here I should put actually the absolute magnitude, and then it's okay. It will be k minus n for k going from n over 2 up to n minus 1. So it's just that for all the k's in the second half, I subtract n from them, and so the last one will be when small k is n minus 1, large k is minus 1. So in this way, I set the variance to be the same in the mode k. There's a certain variance for the mode 0, then I set the same variance to be in the mode 1, k equals 1, and in the mode k equals minus 1, or n minus 1. So this is what I'm going to assume for the variance. And I think we should take a break. So what we will do next after the break is discuss the case first where actually there is no convergence, where m is simply equal to n, because it's easier. After you understand that, you will be able to deal with the case where m is smaller than n, and most of this we will do it in your homework, in the last exercise of the course, question 4 of the last exercise. Okay, so let's take a break.
נוכל לעשות את זה אחרי השיעור. נוכל לענות על השאלה אחרי השיעור.
Yeah, we should be able to. After. זו אובזרבציה אמפירית, לא פיתחנו את זה.
מה זה אומר?
זאת אומרת שאם תקחי תמונות טבעיות, תסתכלי כמה וריאנט יש תסתכלי טרנספורם פורייר. תסתכלי כמה וריאנט יש במקבלי פורייר שונים. תראי שזה סטטיסטיק, זה קטן עם התדירות. באופן הזה. זו אובזרבציה אמפירית. זה לא משהו שאנחנו יכולים לפתח.
לא, אני יודעת כמו זה בעצם, נגיד זה ככה.
אני לא מזדהה עם זה.
אנחנו לא מייצגים טיפה כזה.
אבל זה 10, 14,
כן, אבל שוב לא חצי את הכל פה. נראה לי.
90? 90?
כן. נראה לי.
חצי?
כאילו כמעט הכל היה כזה מסוים מסוימים, אבל אז פתאום זה...
חצי זה יותר מדי.
הסתכלת רק על הרעיל, או רק על הזה, או שזה ש...
הסתכלתי על ההפרש, כאילו ההפרש של value, ואז...
אחר כך, רק זה. רגע.
זה רק היה שיטה לסדר את הראש בזמן שהסתכלים אחרים.
כן, אפשר להספיק לכתוב הרבה מאוד. ולהקשיב. כן, זה כאילו זה עוד שבוע, נכון.
מהוקטורים של המודל קצת פחות, בהרבה פחות גנגליון, ואז כאילו הוא דיבר על עוד משהו של רוטיישן חוץ מזה.
נראה לי הוא אמר על רוטיישן בלבד, הוא מדבר על זה, שמה הוא אמר חוץ משל פאולו? יש את הרוטיישן האסימטרי, כן, והרוטיישן האסימטרי, ופאולו הוא אמר עכשיו ולא היה עוד משהו. כן, זה שני הדברים, אולי הוא אמר זה בגדול היה, שבסיסי הוא יהיה הוא האייגנמטר. כן. כאילו שזה כאילו בגלל שכל סדרת כאילו כאילו איזושהי סיבוב של המודל כאילו צריכה להיות סימולטית ואין משהו מתוקף את הסינים שלהם ואז כאילו את מעבירה את זה כאילו ואז הפאולו אומר שתבחרי את הדמות שהיא כן, כי אלה מאושרות בווריאנט גדול, זה מהפאולו. כן, אוקיי, למה בעצם אנחנו עושים את הווריאנט הגדול? כי כאילו תחשבי שאם יש לך נניח זה הסיגנל שלך, אז כאילו זה יהיה כיוון עם משהו מאוד חזרה. כן, ואז נגיד אם יש לך input noise ואת כאילו מוצחת דברים, אז את לא רוצה למתוח את האינפוט, אז את כאילו no? Thank you. Just saying that like we choose the component with the highest variance because if we have like an input noise and we don't want to stretch it, so like we are stretching in a way that we get the highest signal but the least stretching. So this is
largest, highest variance connected to the lower frequency. Why?
Because this is how we do like you measure it.
Okay, you can. Wow.
Yeah, if you can just take natural stimulus, natural images and we transform them and yes, סרטונים ממש טובים they are very good YouTube stuff that explain why the variance is very good. When I first looked for that, it really made me understand that. I think you can also just do the experiment. It's really easy. You can just take images from your computer and Fourier transform them and then process it. It's difficult. What? It's not very difficult. No, you can say it's taken advice projecting no, but I was saying that you can just check with it and yeah. Observation yeah, but this is because of the experimental yeah. The video, yeah. We did it in like our computational course. Today I'm presenting in all classes.
Yeah.
Yesterday in physiology, Gil presented, and then at the end of the lesson, Mickey asked, like, okay, can anybody like summarize? Gil, can you volunteer someone? And then he said, yeah, I volunteer Noga. And then Mickey made me come here and like summarize his
The thing is
presentation.
that it sounds like a joke when he said it. Like,
No.
like you will choose someone randomly, so I like, yeah, sure, Noga, come. And I was always like, not serious, you know, like. What? I presented the paper, and then you want to make sure that everybody understood like everything. So, but he said it with a smile, and I was sure like he was like laughing.
I think he thought he was joking.
Yeah, I
thinking
think
he was serious.
I
don't
like
think Mickey
volunteered
realized.
Noga, and it is like so automatically without thinking. He's like, yeah, Noga.
Mickey has developed a lot of different teaching skills. Yeah, gradually.
I was scared because
because she's gonna present in Thursday,
Yeah, I'm presenting.
so I should like prepare her article also very well, so
Yeah.
for a case.
In case she automatically picks someone else.
Yeah.
Yeah.
She never did it before, so I didn't really give
I think I will like put in the presentation and I'll give for the conclusion.
לא יקרה.
לא יקרה?
לא יקרה. תגידי, את הבנת מה זה ה-power invariant הזה? נורא רוצה לשיעור?
ה-power law?
משהו על ה...
Translational invariant?
לא, זה משהו הקודם. משהו עבר על שחזקה לא משתנה.
בוא נתפוס איפה.
משהו לא הבנתי, זה מה... כאילו, אומר שאם תשני את ה...
נראה לי שאומרים,
טיימקוד,
אם תעשה
לא כזה כטיימקוד, אבל
אם
כאילו...
תעשה זום אאוט, אתה לא תשים לב, לדעתי זה מה שזה אומר.
זה מה שהתכוון שכאילו... מה שלפנו לב, מה, תלוי כמה על איזה טווח אני אסתכל.
נראה לי שזה אומר שזה לא. כאילו שזה נראה אותו דבר אם אתה זום אין וזום אאוט.
אם יצא מלא זום אאוט, לא נשים לב ששום דבר ישתנה בעולם. נראה לי, לא?
אני אראה לך מה אני מבינה.
חושב שניסנת.
לא, אבל אני חושבת.
אוקיי, עשית ניסוי.
איפה זה? Wait, האינטרנט פה איתי? בוא נעשה x בחזקת מינוס 7.
לא.
זה פאוור. כן, זה פאוור או שזה היה משהו אחר?
זה פאוור, כן, כן. הוא עשה את זה עם E, לא?
מה?
הוא עשה את זה עם E ויחזקה יורד. הוא עשה את זה עם E ופאוור של נגיד...
לא, זה מה שלא פאוור. E בחזקת משהו זה לא פאוור.
מה?
E בחזקת x וטאו?
למה E זה לא פאוור?
כי זה משהו אמר שזה דוגמה למה שלא. זה מחוק.
מה?
הפאוור
אנחנו מבינים את הקטע הזה של ה...
כן, הבנת?
כן, זה מבין. מה זה
משהו נכון, זה מתאים כאילו?
כאילו, מה זה יודעת עצמך?
סתם לראות כאילו מה זה אומר, מה שעושים זום אין זום אאוט זה לא משנה.
עכשיו, זום אין, זום אאוט, זה סקאלה אלגוריתמית?
לא הבנתי סתם.
לא, זה לא סקאלה אלגוריתמית, בסדר.
אוקיי.
אז הפונקציה הזו, את יודעת שהאזור שבו היא יורדת לאפס זה האזור הזה. אז אם אני אציג לך, תוכלי להבדיל באופס. זאת אומרת, עושה זום אין זום אאוט. כאילו, אני לא עובד לך את הצירים, אני אשאל אותך באיזה סקאלה של זום את מסתכלת עליה. תוכלי להגיד לי, כן, נכון?
לא, אני לא באיזה סקאלה של צירים.
זאת אומרת, אם אני לא אראה לך את הציר, ואני אגיד לך, לקחתי את הפונקציה וראיתי אותה באיזושהי סקאלה על הצירים.
סקאלה, אם זה אינפורמציה שאני יודע בדיוק מה היא, x בחזקת 6? אוקיי.
לא, יחסר שזה לא יעבוד, אבל ב-e במינוס x נגיד. e במינוס x, ואני אספר לך, אני מראה לך את הפונקציה e במינוס x, אני רק לא מספר לך מה הסקאלה שבחרתי בתור ציר x.
אוקיי.
אתה תוכל לזהות מה הסקאלה שבחרתי בציר x.
רגע, e במינוס x כן יעבוד ו-e ב-x לא יעבוד?
e ב-x גם יעבוד. אבל x בחזקת בריבוע לא יעבוד. x בריבוע למשל, לא משנה איך אתם מסתכלים עליו, אתם עושים זום אין, אתם עדיין רואים פונקציה שנראית ריבועית, אתם עושים זום אין, אתם עדיין רואים פונקציה שנראית ריבועית.
רגע, אז x בריבוע זה כן דוגמה טובה?
x בריבוע זה דוגמה טובה למשהו שהוא סקייל אינבריאנט.
בוא נעשה.
אוקיי.
אנחנו צריכים להתחיל את השיעור.
רגע, x בחזקת 6 זה לא דוגמה טובה?
כן, כל חוק חזקה. כל חוק חזקה, והדרך לראות את זה היא שאין פה... כאילו, איך אפשר לראות את זה? x בחזקת איזושהי חזקה אלפא.
מה טיפה שונה?
זה עד כדי סקאלה בציר y, כאילו, אני אסביר את זה. x בחזקת אלפא, יש כלל שתמיד צריך לזכור שכותבים פונקציות אם אנחנו חושבים על x כגודל בעל ממדים, אז בכלל אסור לי לכתוב דבר כזה. הייתי צריך לכתוב פה x חלקי x0 בחזקת אלפא, כש-x0 זה איזשהו גודל עם ממדים של אורך. עכשיו אני אומר, הדבר הזה בעצם אני יכול להוציא את ה-x0, לכתוב אותו בתור חלק מהמקדם, זה 1 חלקי x0 בחזקת אלפא, כפול x בחזקת אלפא. אז עד כדי המקדם, ההתנהגות של הפונקציה הזאת לא תלויה, כאילו, ה-x0 לא משפיע בכלל על ההתנהגות של הפונקציה הזאת. היא תמיד נראית כמו x בחזקת אלפא, לא חשוב מה הוא ה-x0. לכן בפונקציה הזאת אין סקאלה. לעומת זאת, e במינוס x חלקי x0, מתנהג באופן שונה, כאילו אם הייתי מסרטט את הפונקציה הזאת ולא הייתי מספר לכם באיזה סקאלה של הציר x אני לא מסתכל, הייתם יכולים לזהות מה הסקאלה, כי אתם יודעים שהפונקציה הזאת דועכת בערך בסקאלה של x0. זה פחות או יותר, אני רוצה להתחיל את השיעור. Okay, so after saying all this is our model. I'm actually going to discuss, which I think is a bit erased now, I don't know why. I'm going to discuss the case where m is equal to n. M is equal to n. And then afterwards I'll say a few words about what changes when m is smaller than n, and you will hopefully finish this, fill in the gaps in exercise, in question 4, the exercise. So, m is equal to n for the factor, the ratio between them p is equal to 1. And so, everything in here so far is within the scope of the general model that we discussed. We have n input neurons, m output neurons. We specify what are the statistics of the inputs. It's Gaussian. We specify the correlation function, the covariance function. And our theory so far tells us, using all these ingredients, it predicts a very large family of possible weights because of the fact that there is a unitary transformation that we can apply to the WPC solution. Now we're going to add to that the assumption of translationally symmetric receptive fields. That's an additional assumption that we did not put into the theory previously. So what does that mean? It means that Wij transpose is some function of j minus I modulo n. And the modulo n is exactly the periodic boundary conditions which came into play, I remind you, both in our assumption about the statistics of the inputs, that this neuron is correlated with the input of this neuron is correlated with this one just as much as these two are. But it's now coming in also in the fact that the projections from ganglion cells now n is equal to n, so we have one-to-one correspondence. The projection from a cell here to the cells here is the same as the projection from a cell here to the cells here. It's wrapping around. It's as if it's all on a ring. Now, what does that mean? It means that the weight matrix has the following structure: W0, W1, W2, Wn minus 1. And then the next row will be the same, just shifted. All right, and so what can we say about the weight matrix? Circulant. So we have two matrices which are circulant in our theory. One is a correlation function of the inputs. I didn't write that explicitly, but the assumptions that I've written here imply that the correlation function of the inputs is circulant. That's why the eigenfunctions of that, the principal components of that matrix were the Fourier components, right? Now, in addition to that, we see that this assumption implies that the weight matrix is circulant as well. I want to draw what this function might look like. The small w's. So you see that this function, the small w's, is all we want to predict now. And that describes the structure of the receptive field of one neuron. And if I know it, I know also the receptive field of another neuron. It's just translated relative to the first one. So I want to draw this because I just want to clarify the notation and what the different values mean. So if this will end up being center surround, then it might look something like this. And in fact, it's all discrete. So this would be W0, this would be W1, this would be W2, etc. And remember that W minus 1 is like Wn minus 1. So actually, if I go here from I going from, or J going from or well, this is Wi, or let's do L. So this will be L. So L goes up to n minus 1. And we expect our function to be, its value for n equals n minus 1, which is like minus 1, to be exactly the same as here. So this is another assumption. This is another ingredient which I did not specify explicitly. I did not specify that the receptive fields will have to be symmetric with respect to this point, meaning that the value here is exactly as here. So actually this function will look something like this. And this is Wn minus 1, and this is Wn minus 2, so on. Well, this is the same as this. This should be, I don't know if it's true in my drawing, but this should be the same as this, Wn minus 1, and then this should be the same as this, Wn minus 2, and so on. Now, but because the correlation function of natural stimuli has the symmetry that it's only a function of the distance and doesn't matter if it's a point to the right or point to the left, it will end up being like this. But in principle, so when we're doing the optimization, we think of each one of these as independent variables. So the symmetry is something that will end up coming out, but I'm not assuming it. And also the fact that it has this structure of center surround will come out of the theory. So this is what this W might look like. I just pointed out that this is the receptive field. This tells us the relationship between a ganglion cell and the photoreceptor right in front of it. So it makes sense to assume that that's the maximum. And I expect if we will end up with realistic receptive field, they have to have center surround structure. So it has to be, if you go to the right or to the left, then the strength of the receptive field will decrease. But going here is like going here because of the periodic boundary conditions. So this point is really like this point.
What you drew now is our expectation.
Yeah, this is kind of our expectation. But I also, another reason why I'm drawing it is to highlight the meaning of the different indices here. That 0 is like the photoreceptor right in front of you, and 1 and n minus 1 is going one step to the right or to the left. Okay, now in addition to all this, we will of course put into the theory the assumptions about input noise, output noise, as we did in the general formulation. And now we need to use the theory to predict the weight matrix. Now the theory tells us that the weight matrix should be the WPC solution up to unitary transformation. And the question is, can we achieve this particular structure of the weight matrix by applying a unitary transformation? It's not obvious. So let's see if it's possible or not. So we're going to use the fact that this matrix is circulant. And I want to remind you that for any circulant matrix, if I take the matrix let's call it W transpose. If I take the matrix and apply to it a very specific unitary transformation, which is the Fourier transform. So I will represent it by putting here a matrix, the matrix that represents an inverse Fourier transform. And here I will put U transpose, which is the forward Fourier transform. And I should actually put here, I should actually put here a U dagger. Do you know the difference between transpose and dagger? Yeah, everyone knows it? Dagger is both transpose and complex conjugate. Okay, so that's the correct. When I discussed unitary transforms previously, I actually should have said that's the way I wrote transpose, but you actually should do dagger if you're dealing with complex numbers. So forward Fourier transform. So if I take a circulant matrix and I sandwich it between the Fourier transform from the right and to the left in this way, I know that I'm going to get a diagonal matrix. And I will call the elements in that diagonal matrix W0 tilde, W1 tilde, up to Wn minus 1 tilde. And let me call this matrix W tilde transpose. Now, why do I say that that's true? This is exactly the statement that matrix that the basis in which a circulant matrix is diagonalized is the Fourier basis. The way to think about it is that if I want to understand the way to think about it is to actually invert. One way to think about it is to invert this relationship. To write that W transpose, I will multiply from the right by U dagger and from the left by U, and U dagger and U dagger U is 1. So I will get that W transpose is U W tilde transpose U dagger. This is a inverse Fourier transform, and this is forward. So this equation, what does it tell me? It tells me that if I want to understand what the circulant matrix is doing to a vector, I can first decompose the vector into its Fourier components by applying the forward Fourier transform. Then each one of these components is simply multiplied by a constant. That's what this matrix is doing. And then I go back and do an inverse Fourier transform. Okay? So the statement that this matrix is diagonal is really like saying that a circulant matrix operates independently on each one of the Fourier components. Again, I want to ask what is W transpose doing on a vector. I can think about it as decomposing the vector into its Fourier components. This is what this is doing, multiplying each one of them by a constant, and then going back doing an inverse Fourier transform. Okay, but that's very nice in our context, because if we look now at this equation, where will I continue to write? Here. If I look at this equation, let me write it again. W transpose is equal to U W tilde U dagger this is Fourier transform. And I ask, what is this function doing to an input vector? An input vector is the activation of the photoreceptors. So I claim that U transpose U dagger X, what is that? That's a Fourier transformation. So it's the decomposition of the visual input into its Fourier components.
I'm just confused because the activation of, I would imagine the activation of the photoreceptor would be a matrix.
Why? It's a vector. The photoreceptors are a vector.
But there are
But we're doing a one-dimensional model of the retina.
Okay, sorry, I missed that.
Right? We're doing a one-dimensional. So that's why, if we go to two dimensions, that's why I'm not doing two dimensions, because it's a bit confusing. Everything can be easily generalized, but it's just a bit. It's still, in a sense, even the visual input in two dimensions, you can think about it as a vector, but it's a matrix also, so it's more complicated. It's more confusing. So we're doing a one-dimensional version. So this is a decomposition of the visual input into its principal components. Then we're applying it to it a diagonal matrix, W tilde. Remember, W tilde is diagonal. So if we would end here, if our weight matrix would be something of this form, what is that form? That's the form of the PC solution, because the PC solution tells us take the input, decompose it to the principal components, and then multiply each one of them by a factor. That's exactly what this is doing. But on top of that, we have a unitary transformation. That's fine, because we know from the start that we have the freedom to apply to the PC solution a unitary transformation. But due to the symmetries of the problem, we know what is the appropriate unitary transformation. It's simply an inverse Fourier transform. So all this must be the PC solution. And this is inverse Fourier transform. Now, there are a few more things that I need to tell you. One is that when I wrote this, this is just a mathematical statement that these W tildes are related to these W's by a Fourier transform. So the elements, when you diagonalize a circulant matrix, you discussed this with Meta, when you diagonalize a circulant matrix, the elements that you get in the diagonal are the Fourier transform of the elements on the rows of the circulant matrix. So there's a one-to-one correspondence, which we know, between these numbers and the receptive field. Okay? Now, we go back to here. If this is the WPC solution, then we know what it should be. Then the elements in this matrix must be the square root alpha i's that we discussed in our theory. So W, if this is the PC solution, then W tilde I, small w tilde I, the elements in the diagonal of this matrix must be the square root of alpha I of the WCPC solution. And we have a set of equations telling us how to find them, right? Remember, we have an expression for each one of them. The alpha I is a function of the lambda I, the input noise, the output noise, and then we have to just make sure that the constraint is fulfilled. So I want to write a conclusion for what is the recipe that you need to follow in order to calculate the receptive fields of the retina. I will do it here. I will do it here. The receptive fields. To calculate the receptive fields, what do we need to do? We need to solve the WPC problem to get square root of alpha I. Okay? That involves our assumption on the eigenvalues, which are the 1 over large K to the power 2 minus eta. And then all we need to do, once we found the square root of alpha I, we map the square root of alpha I to the Wi tilde. And what do we need to do to get the spatial receptive field? Just inverse Fourier transform. Now, there's one subtle issue that I kind of ignored, and I write it down here. In principle, the fact that this is diagonal still leaves me a freedom. I told you that the structure that I want to get, a circulant matrix, implies that we can evaluate these W's precisely, uniquely. But it's not absolutely true. We still have there's still one type of unitary matrix that in principle we're allowed to apply here, which will leave the matrix as circulant and will not break any of our requirements. And this is to take each one of the elements here and multiply it by a phase. So in principle, I will write it down. We have freedom to choose Wi to replace Wi by e to the I phi I square root of alpha I. So I told you, that the prescription was we set Wi tilde to be square root of alpha I. But I claim, in fact, we can do this, where we can take square root of alpha I and multiply it by a pure phase. Okay? Because what matters is just the absolute magnitude of Wi tilde, not the phase. We would need to choose this phi I to be the same for I, and minus I would need to choose opposite phases. But otherwise, we have this freedom. And so that seems to break the... This means that we actually have a family of receptive fields, still have a family of receptive fields which are compatible with our theory.
What would be the difference? I mean, just shift it.
Okay, so no, but, well, in principle, each one of these phi's can be chosen independently of the others, except that phi 1 should be minus phi minus 1. I'm not getting into that detail. Phi 2 has to be, in order to get eventually real function.
I'm just not
But
sure if I understand how it affects the way.
it's a good question. Not clear, right? You take a function, you multiply each one of its Fourier components by a phase, and then you do an inverse transform. What happens? Something happens to the function. So there are many different functions which are compatible. So now the question is, are we lost? Are we still not able to predict the receptive field? And the answer is that there is an assumption, that additional assumption that comes to the rescue. And this is that our assumption is that the retina is trying to make the receptive field as compact as possible. Meaning that the range of photoreceptors to which each ganglion cell needs to connect to is as small as possible. That makes sense as an architectural constraint. In terms of the mutual information and our constraints on power and all that this transformation doesn't change anything. Okay, it does not change the amount of information conveyed, but we want to choose the structure of receptive field which is the most compact. So we can prove that most compact receptive field is obtained by phi I equals to 0, all phi I equals to 0. This is special because square root of alpha I is real. This is real. So this means that we just choose all of these to be real. Okay? And this is the choice that will make the receptive field more compact. In fact, it's not precisely true. More generally, we can choose phi I proportional to I. And I will explain why we can choose that as well. Do you know what happens if you... phi A J proportional to J. Do you know what happens if you multiply a function by a phase that just increases with the frequency in that way? Does anybody know? If you take a function, you Fourier transform it, and you multiply each Fourier component by a phase that increases linearly with the frequency. Do you know what you get? Anybody? What you get is translation. So this just, if I would choose here a phase which increases with J, that would just correspond to taking the receptive field and shifting it. And of course that's allowed because it just means that it's like a redefinition of which ganglion cell is in front of which photoreceptor. I tell you what is the receptive field of the ganglion cells. I could just as well decide that ganglion cell 1 has the receptive field that I previously called the receptive field of ganglion cell 2. It's just a shift. So this really doesn't mean anything. Of course, we will want to choose that. So with this phase phi equal to 0, it's also that the maximum will just be at, in front of each cell. And if we choose that, it will be just like a shift, the circular shift of the receptive field. So that's not interesting. So just to sum up what I'm saying, or reiterate what I'm saying, the whole recipe tells us that we need to calculate the square root of alpha I and plug them in as a Wi tilde, and then do an inverse transform to get the Wi. In principle, we could have taken something like this, but if we want to require that the receptive fields are as compact as possible, that means that these phases are real, are all one, just one, that e to the I phi I is just one. Okay, so phi I equals 0. And it's a nice exercise to try to prove this if some of you want to do it, but if you want to try. And that's it. So
Can you can you define compact again?
yeah, here I deliberately didn't want to go into it because the way to define it in order to get this result is by asking what is the like calculating something like a variance relative to the center of mass of the receptive field. It's like a measure of the spread. You define a measure of the spread of the function, and if you want to minimize that, that tells you that you want to choose the phases like this. And the particular choice which is most convenient is to choose them just to be all of them same. And that's it, okay? So I think I will not continue to answer questions because we really need to discuss a bit also the case of m smaller than n. But this is the recipe for what you need to do if m is equal to n in order to calculate the receptive fields. And I just want to briefly say what does this determine? What does the square root of alpha I determine in the end? One thing that you see they determine is the structure of the receptive field because of what I wrote here. We take the square root of alpha I, we inverse transform this, and this gives us the structure of the spatial receptive field. But the square root of alpha I have another important implication that you will explore, I hope, a little bit in the exercise, and that this is really telling us what amplification factor the visual system is applying to each one of the Fourier components of the signal. And eventually this affects the perceptual thresholds for identifying grating. So I remind you, last week on Thursday I showed you very old psychophysical experiments from the 1960s, or maybe this was even the end of the 50s, Van Ness and I forgot the other name. And they looked what are the perceptual thresholds at which human subjects can identify a Fourier grating at different frequencies. And so we have the input, it's corrupted by noise, and then there's output noise. And we amplify different components by different factors, and then they get corrupted by the output noise, so their perceptual threshold will depend on the amplification factor and on the variance that existed in the so yeah, not just on the amplification factor. So if you know what are the square root of alpha I, you can predict what will be the and what is the input noise, the output noise. You can predict what will be the perceptual thresholds for different frequencies. So what I want to just tell you now, because we don't have time, is that if we do all this exercise, what you find is that the theory, first of all, predicts that for low input noise, you indeed get receptive fields that look like this. For larger input noise, you get receptive fields which are not center surround. They don't have this negative part. Okay? And in addition, if you use the theory to predict the perceptual thresholds, they have the behavior that is observed in experiments. And this is what Attic and Redlich showed, and you will do this in the exercise for the one-dimensional retina. Next, on Thursday, just at the beginning of the lesson, maybe I'll show you receptive fields that you get from a theory like this in 2 dimensions. Right now, we don't have time for that. So what I want to do next, I will need to finish a few minutes late, is discuss very briefly the case of m smaller than n, and how it's different from what we've done here. So when n is equal to p times m and is larger than m, or p is larger than 1, then what can we say about the weight matrix? Then the weight matrix has, an n by m structure. And if I would write now the receptive field of the first neuron, W0, W1, Wn minus 1, how would the receptive field of the second neuron look like? Shifted by p. Now it will be shifted by p. So we will have here, if this is WP, then W in the second one it will be like this. And so on. So this is the main difference between this case and the previous case. Now, this is not a circulant matrix. This is a type of matrix that you discussed with Neta in the last TA session. This is a generalized circulant matrix. So let me just write down what is the prescription that needs to be done in order to evaluate the receptive field. And this, to understand this better, you will do the exercise. First, find square root of alpha I for first